All right, at this point, we have pretty much all of the derivative rules that we're going to need to know with the product rule, quotient rule, chain rule, all that kind of stuff. But now we just want to tinker with our idea of what it means to differentiate something. So we're going to talk about implicit differentiation. And what I want to do right off the bat is just start talking about what the difference is between something that's implicitly defined or explicitly defined. We're going to be talking about functions right now. And an explicitly defined function is something where we can see the relationship between the output and the input directly. If you remember, a function is something where you put in an input and you get a single output as an answer. And so here we can see exactly what the relationship is. If we put in our input, anything for x, we have to multiply that number by 4, subtract 5, and that's what our output will be. If we have an implicitly defined function, we could write it something like this, where you'll notice that we don't have this solved for y, meaning we're not telling exactly what the output is going to be for a given input. It's the exact same relationship. You can see that all I've done is subtracted y from both sides of our equation. And so this equation is the exact same thing as the one that's explicitly defined, but it doesn't state directly what's going on in terms of y. Now, with something that's explicitly defined, it's pretty easy to find our derivative because we know all of our derivative rules. And in this case, this is a pretty basic function. We can see our derivative is going to be 4. With implicit differentiation, what we want to do is be able to take something that's implicitly defined like this and get this same derivative using a different process. So bear with me for a second. Let's deal with that. The first thing that we're going to do, and really the main thing that we're going to do, is we're going to recognize that the derivative is like an operation that we can apply to an equation. Just like we can add 6 to both sides of our equation and it stays the same, or we could subtract a number from both sides of our equation, or divide or multiply on both sides of our equation. What we can do is we can take a derivative of both sides of our equation. So the derivative, maybe I'll put that in parentheses as well, of this whole left side, 0, is equal to the derivative of the right side. Basically, we're saying that if these two sides are equal to each other, then the derivatives, or the slopes, are also equal to each other. What we can do now, though, is say this really means the derivative of 0 is equal to, I'm just going to use that sums and differences rule to say I'm looking at the derivative of each of these terms. The derivative of 4x minus the derivative of y minus 5. And at this point, oops, sorry, I need a derivative here. There we go. Minus the derivative of 5. At this point, we can just start finding the derivatives of each of the pieces, each of the terms, pretty easily. Most of them are not difficult. Most of them look exactly like things that we've already seen. So for instance, the derivative of 0 we know is 0. The derivative of 5 we know is also 0 because that's a constant. The derivative of, maybe I'll just do this. The derivative of 4x is 4. And this is really the only one that's a bit different here. When we talk about the derivative of y, every now and then people will want to say something like 1 because that looks like it could be a variable and the coefficient is 1. Every now and then people will say, well, wait a second, that doesn't have an x in it, so is this kind of constant? So is the derivative 0? And the answer is neither of those things. When we talk about the derivative of y, specifically the derivative with regard to x, that's what this dx means, and I'll explain that later. We can just use notation for that. We can just say that's dy over dx. Or, if you'd rather, and what we'll probably do, is say that's y prime. At this point, I guess maybe I'll put minus 0 so we can see that. At this point, it's pretty easy to reorganize this, add y prime to both sides, and we get y prime is equal to 4, just like we did when we did explicit differentiation. So again, to recap, with implicit differentiation, we differentiated each term on both sides, and we just had to be careful about the term with the y in it. Now, here's the real question. Why do we care about this? It's way easier to differentiate that function in the normal way, solving it for y and going on from there. The main thing to notice is that we may not always be able to solve for y. So if we're thinking about it in the normal way, we might not be able to do that. Specifically, if we have something that's not actually a function, then we won't be able to write it explicitly in terms of y, because for it to be a function, we have to have this one input connecting with one output thing, and that means that we won't be able to have a nice y equals something. There's some other reasonings there, but we're not going to go into it too much. But the main idea is that this is going to unlock the ability to look at derivatives of things that might not be functions. So first, a couple of notes. Y, we normally think that it's like a function of x, but here we're going to not restrict ourselves to it being a function. So really we're going to say there's a relation between y and x, and it does not have to be a function relationship, meaning we can have one x value going to multiple y values now. Because we don't have to make this thing a function, it just has to be an output of x. It's still going to act like a function, though, in how we treat it. Dy over dx is the same as y prime, but I like this notation here. I'm going to use the d over dx, the derivative notation, and I'll every now and then use dy over dx, because it tells us what the input and output is. The thing on the bottom here is going to act like the variable or the input, and the thing on the top is going to act like the function or the output. That's going to be helpful. When we differentiate y with regard to x, we'll have to treat it like a function of x, even if it's not actually a function of x. So what that means is that we have to say the derivative of y is something like y prime, or dy over dx. Or we can say if y is on the inside of something, that's like a function on the inside of something. And so we might have to use the chain rule. If there's a combination of x's and y's in one term, like a product of those things, we might have a function y times another expression, and so we might have to use the product rule. And then at the very end of all this stuff, we're going to try and isolate this for y prime. That's our goal, to have this thing solved for y prime at the end, because that way we'll have our derivative. What we'll notice is that a lot of times our derivative will end up being a function, even if the equation that we're working with isn't. So y doesn't have to be a function of x, but a lot of times we'll notice that y prime can be. It might not always be, but it can be. Anyways, here we go. So here's a classic type of setup here. We've got this circle. This is the equation of our circle. I expect that we've seen this x squared plus y squared equals r squared setup. That's the circle with radius r. So this is radius 3 on here. And maybe we want to find the equation of the tangent line when x is 2. First off, we will notice that this is clearly not a function. When x is equal to 2 here, this thing fails our vertical line test, because we've got this vertical blue line passing through both of those points. We can see the tangent lines on there. We can see that there's 2 of them. We're going to get multiple slopes when x equals 2. In this case, we can see the slopes of these red dotted lines are different from each other. So before we get into any sort of equation of tangent line thing, what I want to do is deal with this equation, this x squared plus y squared equals 9, and I'm going to find dy over dx or y prime. This is typically how I'll state things on quizzes and tests. You can use this differential notation or the y prime. It doesn't really matter. But the first thing that we're going to want to do is differentiate both sides. I'm going to skip a little bit, and instead of just writing d over dx times the whole left side, I'm going to just look at the derivative of all of the terms individually. That's what we're going to have to do anyways. And now we can just start finding derivatives when we know them. The derivative of x squared is 2x. The derivative of 9 is 0. And now we have to be careful with this. The derivative of y squared certainly is 2y. But notice we're talking about some chain rule here, because y is a function. So this is really like 2 times, or sorry, let me get rid of that. This is really like finding the derivative of 2 oh my goodness, I keep writing 2, and I want f of x, squared, where the derivative is going to be 2 times f of x, but then we have to multiply by the derivative of that inside function, f prime. Here, instead of using f of x, because that means it's a function here since it's not, we'll just do y prime. Every now and then people will put dy over dx here instead, so it might look like this. Both of those are the exact same thing. It doesn't really matter to me which one you use. At this point, we want to solve this thing for y prime, or for dy over dx, which is not very difficult. Let's subtract 2x from both sides. And now we can divide by 2y, and we've got y prime is equal to, I'll just say negative x over y, because those 2's will cancel out. So that is my derivative. Oof, that's brutal. There we go. That's good enough to be boxed in. So what this will do is this will tell me the slope of the tangent line at any point on this circle. Notice my derivative is written in terms of x's and y's. Here, we're told to find out what's going on at x equals 2. What you'll notice is that we're going to need the y value here. So that's something that we'll have to just kind of notice. So again, if we're trying to find the equation of this, maybe I'll write the, I'll write the derivative here, negative x over y, I believe it was. Yeah. So that was our derivative that we found. If we want to find the equation of the tangent line, notice that we'll need to find the y value here. There's 2 of them. We can find this by taking x, plugging it into our equation, and we've got 4 plus y squared equals 9. So we have y squared equals 5, or y equals plus or minus root 5. So that's what these 2 y values are. So let's just pick the positive root 5 here. I'll let you do the other one afterwards. At this point, we need a slope. The slope is going to be the derivative. It's going to be y prime, and then I'm going to show you some new notation that we have. Since we used to do things like, I'll write it over here in red maybe, we used to find things like f prime of 2 and things like that, where we'd put the x value in here. We use this function notation. We have to come up with a new way of defining how to evaluate a derivative when we don't need just the x value. What I mean by that is that here we have to use the actual coordinates because we have 2 points where that x value is 2. And you'll notice we also need to know what the y coordinate is here. So we use this vertical bar. This vertical bar means like evaluated at, and then we write this in here. If you want to see some more of that notation, take a look in your textbook, you'll see it. But it means exactly what you'd think it means. It means put in 2 for x, so this is going to be negative 2 over root 5 for y. So there's our slope. We've got an x value here and a y value. So what that means is that the equation of that tangent line is y equals negative 2 over root 5 x minus 2 plus root 5. We can go ahead and multiply all this stuff out. Negative 2 over root 5x plus 4 over root 5 plus root 5. What's that going to be over root 5? That's going to be 5 over root 5. So this is really going to be y equals negative 2 over root 5x plus 9 over root 5. That is the equation of this tangent line. Notice the only thing different to find the equation of the other tangent line is that the y value is going to be negative. That's going to change your slope because you have to use the y value for your derivative, for your slope. And it's also going to change this y value over here. So use the derivative there to figure out what's going on with that other tangent line. See if you can find how that works. But it's really going to be the exact same thing. So that's how the chain rule works. When we see some stuff going on with y, we'll want to make sure that we can, make sure that we multiply by that y prime again. So just to remind us of what that looked like, over here, that chain rule was coming in right here, or if we're using the differentials, right here. The derivative of y squared is 2y times the derivative of the inside function. Even though y is not a function, it acts like it. All right, let's talk about the product rule here. Let's just find the derivative here. We're not going to worry about finding equations of tangent lines or anything like that. It's going to act the same way. For this curve, we'll go ahead and find dy over dx or y prime. So let's differentiate both sides. So I'm going to use d over dx y minus d over dx x squared y plus d over dx 5x equals d over dx, oh boy, let me fix that x, of 0. Most of these, again, are going to be pretty easy to find the derivatives of. So we'll just take it step by step. The derivative of 0 is going to be 0. The derivative of 5x is 5. I'm going to skip over to this first term here. Maybe I'll draw my little arrows down. The derivative of y is not going to be 1. It's going to be y prime. And now this one, we're going to have to do a product rule on. Notice that we have two things being multiplied together. We've got x squared and we've got y. Since y acts like its own output or a function, even though it's not necessarily a function, what we can do is separate this term into x's and y's. And now we can find u prime, which will be 2x, and v prime, which will be y prime, because the derivative of y, again, is y prime, not 1. Now our product rule says multiply these things together. So I'm going to put all of this in parentheses because we're subtracting this whole thing, and what we have is 2x times y plus x squared y prime. At this point, we're pretty much finished with the hard work. Now it's just algebra and solving things. So we're going to say y prime minus 2xy minus x squared y prime. I'm going to put that negative across everything. Plus 5 equals 0. What I want to do now is solve this for y prime. So I'm going to take my 5 and my 2xy and move them over. Minus x squared y prime equals 2xy minus 5. Now, notice that y prime is a common factor here. So if you factor it out, I'm going to move over here, we end up with y prime times 1 minus x squared equals 2xy minus 5. And so now it's pretty easy to solve this for y prime. We're going to get y prime equals 2xy minus 5 over 1 minus x squared. I know I got boxed in the corner here, but we're essentially going to just factor it out and then divide by the rest of that stuff. Every now and then it's weird to figure out how to solve for y prime here when there's multiple terms with it. But as long as we isolate them by themselves on one side of the equation, factor out the common factor of y prime, and then divide by the rest, things should be good. So here's your quick summary. If you want to pause this to jot it down, this might be helpful. But I'll just kind of go through it. We're going to use the chain rule whenever we have an expression involving something where we're like doing something to the dependent variable, which we're going to call y most of the time. Other than multiplying it by a coefficient. So what I mean here is like if we had e to the y or natural log of y or y to the fifth or anything like that. We've got y on the inside of a function. What we're going to do is we find the derivative of the term with the y in it like normal. What I mean by that is we just treat it like a regular variable, and then the chain rule says we have to multiply by the derivative of the inside piece. Our inside piece is y, so we end up multiplying by y prime. So the derivatives of all those things are things like y prime e to the y, y prime times 1 over y, and 5y to the 4 y prime. The derivative of e to the y is e to the y, but then we multiply it by y prime. The derivative of natural log of y is 1 over y, but then we multiply by y prime. The derivative of y to the fifth is 5y to the 4, but we multiply it by y prime. So that's the chain rule. It ends up being pretty easy once we get the repetition. It takes a while to get used to it. But the moral of the story is whenever you're doing something with y in it, do everything normally and then tack on an extra y prime at the end. The product rule we're going to use whenever we have an expression that includes independent variables and dependent variables. Basically, whenever you've got x and y together. Set up your u's and v's. I always make the u all the x stuff, and then I'll try and simplify all the y stuff to be like just y, or if it was a y squared in there, whatever. And then make sure that you can kind of separate those into your u primes and v primes and all that stuff. But the product rule, you're going to notice that you use it whenever you have a combination of x's and y's together. At the very end, to solve for y prime, it's really 2 or 3 steps. Get all the y prime terms together on one side of the equation, everything else on the other side. Then pull out a common factor of y prime, then divide by the rest to isolate. Here's a couple of examples. I think I've got, just the 2 here. Give these a shot and then come back and see what's going on. Before we do that, maybe we can identify what we've got going on here. For this first term, there's a chain rule. Here, we've got a product rule. The reason I know that is that the chain rule says that there's something on the inside. Y is a function. We're doing something to it. This one I know it's a product rule because we have a combination of y and x together. Here, I can see another product rule. And this one is a bit weird. We're certainly going to call it a chain rule because there's stuff inside of that log, but there's a product rule happening as well with the x and y. So this is like a product and a chain rule together. Give that a shot. Come back in a second, and or pause the video if you want, and then come back and we'll see what we've got. All right, hopefully this is what you did. We're going to take a derivative of everything. I'm going to try and write small so that I can fill it all in here. Oops, I forgot my derivative on x to the 5. There we go. So we put this d over dx in front of everything. This notation is very important because later on we're going to change what the variable is. And so for now, I would really recommend putting the differential d over dx in front of each of the terms, even though you're just taking derivatives of things. Even though it's easy to skip from x to the 5 to 5x to the 4, write that d over dx in front because it's going to be really important later on when we talk about related rates. Anyways, let's go through each of these. We know there's a chain rule going on. So hopefully you found out that the derivative here is 2y, y prime. There's a product rule happening here. U is y and v is e to the x. So u prime is y prime and v prime is e to the x. So we'll go ahead and put all those things together. Since we're adding it, I don't have to worry about putting things in parentheses because I don't have to distribute a negative. So we're going to have y prime e to the x plus y e to the x. There's our product rule. The derivative of x to the 5 is 5x to the 4. And the derivative of 0 is 0. So now we're at the point where we can do this stuff. We're going to get all the y prime terms together, these two. So what that means is we're going to subtract both of these terms. We're going to put them on the other side of the equation. So we've got, 2y prime plus y prime e to the x equals negative y e to the x minus 5x to the 4. Now again, notice y prime is a common factor. So let's factor it out. So we've got y prime times 2y plus e to the x equals negative y e to the x minus 5x to the 4. And now we can divide by 2y plus e to the x. And we end up with y prime equals all this stuff. Negative y e to the x minus 5x to the 4 over 2y plus e to the x. Something like that. If we wanted to evaluate this at a point to find the slope of my tangent line, I could just plug into different x values and y values. Notice you'll need the y value here to figure out what's going on. Every now and then, people will, or situations will give you just the x value, in which case you would have to go back to this original equation here, plug in the x value, and solve for y. Notice that if we had an x value like 0 or something like that, and we put in 0, we'd get y squared plus y equals 0. You could factor it and then you go from there. This is a quadratic equation now. So this might be a case like that circle where you end up with more than one point here. But, oh well, easy enough to do. That's all just algebra. Hopefully we're okay with that. All right, second one. This one is going to be a little bit trickier with this product chain rule combination. Well, maybe not. I don't know. We'll see. We're going to take a derivative of everything first. So let me write that all out. The derivative of y natural log of x, and that's going to equal the derivative of 4x. Now, let's start with this one here. We've got this box on the inside of our natural log. So we know that the derivative is going to be 1 over xy times box prime. But now the derivative of that box is going to be a product rule, where u is x and v is y. So u prime is 1 and v prime is y prime. If we put those things together, we're going to get x y prime plus y. Similarly, I'll do this one in blue. We have another product rule here where u is y and v is natural log x. So u prime is y prime and v prime is 1 over x. So we end up with plus y times 1 over x. So maybe I'll just say y over x plus y prime natural log x. And my derivative of 4x is 4. I'm going to put this all together into fractions and stuff like that. I'm going to say x, y prime plus y over xy plus y over x plus y prime natural log x equals 4. All right, you could start moving things around and all that kind of stuff to solve for y prime, but what I'm going to do is get rid of these fractions. The nice thing about this is that this is still an equation, and so we can still manipulate it the way that we want. So what I'm going to do is I'm going to multiply by the denominators here. I'm going to multiply everything by xy to get rid of those fractions so that I don't have to worry about them. You can do this at any point from here on out. I think it's easiest to do right off the bat. So if I multiply everything, maybe I'll just write this out here. I'm going to multiply by xy, and there I'll multiply by xy as well. So here I'm just going to have xy prime plus y, because the xy will cancel out. Here the x will cancel out, but I'm going to have an extra y, so this will be y squared. And now this will be xy, y prime natural log x, and this one over here will be 4xy. Now I can just move things around to get my y prime terms on one side and go from there. So I've got x, y prime plus y plus x, y prime natural log x equals 4xy minus y squared. And I'm going to erase some stuff so I've got some room. I think this will actually work a bit better. There we go. So what I'm going to do is skip some stuff and I'll just have this solved. But you can go ahead and figure this out. Hopefully you end up with y prime equals 4xy minus y squared over x. Oh, wait a second. Let me go back. I realized I forgot to do something. There's this plus y here. I'm going to get rid of that and subtract it from the other side. Sorry about that. I missed that term. So let's make this minus y now. So we're just moving this one over as well. All right, so now we'll end up with y prime equals 4xy minus y squared minus y over x plus xy natural log x. If you want, you can try and pull out a common factor of y here. You notice it won't cancel out in the denominator. Every now and then you can find things that will cancel out, but this is about as good as we can leave this here. It's a pretty ugly looking derivative, but again, if we have some x and y values, we can just throw those into this equation for our derivative, evaluate it using that vertical bar notation, and see what happens. Hopefully that's a good start for implicit differentiation. There's a lot of really good examples in the text. Jump into those, get some practice on them, ask any questions that you've got on the discussion boards. But again, we're really just keeping an eye out for the chain rule and the product rule here. Notice that we don't have to worry about the quotient rule, because if we ever have division like this, just multiply both sides of the equation and get rid of those denominators. Then you don't have to worry about it. All right, good luck. Try some of those problems. Let me know if you have any questions.